Bom dia a todos. Okay, good morning, everybody. Welcome to our first session of the day. Our first speaker is Valentin Souder, who will be speaking about an equivalent representation of generalized differentials. Valentin.
Thank you very much. I don't think the mic is working. Yeah, right. Can you hear me now? Okay. Thank you all for coming. Today I'm going to talk about generalized differentials, and actually my presentation is going to be in two parts. The first part is going to be about not something very deep, but like something more like a curiosity, and then I'm going to lead to a more general, maybe more interesting question that is related to generalized differentials. Okay. So first, what's a differential? Differential is, well, you take like the function f, and in a direction alpha, you just look at the differences in the images, right? And it's kind of like a derivative, so I'm going to use differential and derivatives kind of interchangeably. The interest where we look at this is from a cryptographic point of view. Like we're trying to minimize the number of solutions each images of the differential have. So the function that has the best differential uniformity are the function that raises the best to differential cryptanalysis. And so this equation has exactly one solution. So like the differentials are bijective. And only when the characteristic of the finite field is odd, because when the characteristic is even, if x is a solution, x plus alpha is also a solution, right? Like this is a plus, and x plus alpha vanishes, and so on. And so in even characteristic, we don't have perfect nonlinear functions. We have almost perfect nonlinear functions, or APN functions. And it's a very interesting topic. There's like a lot of results about this. And that's been my main research topic for like many, many years now. So, okay, so we have differentials. When we differentiate, we can differentiate again and again and again, and we can compose differential like this, and we call them like higher order differentials. And essentially, when you take a bunch of directions like this, you end up with like quite an ugly alternated sums, but this is what it is. And we call them differentials because the algebraic degree, which is when you look at the function f as a vectorial function, so as multivariate, it's like the multivariate degree is kind of decreasing every time you differentiate. It's kind of like the intuition of why you can consider them derivatives. Okay, so maybe a little example. When you derive twice, you derive once, and then you can differentiate another time, and you end up with like the alternated sum. When you do it 3 times, you do it once, twice, 3 times, and then you end up with like this sum at the bottom here. What's interesting is that when the characteristic is even, all of the minus becomes pluses, and essentially what you're doing is you're summing the images of an affine subspace. So it's very convenient, and like everything works very well. When the characteristic is odd, though, well, first you have minuses, and it's like it becomes an alternative sum. But then you also like sums elements, the directions. Like you see, you have like all of the 3 directions, and then like 2 out of the 3, 1 out of the 3, and like the f dx at the end. And so you end up in odd characteristic, you end up with like an alternated sums of images of F2 combinations of F2 elements, and it's kind of awkward, right? And intuitively, I believe this is why differential cryptanalysis doesn't quite work in odd characteristic, because like computing this sort of higher order differential is very expensive in complexity, and so you lose interest in the cryptanalysis. So we had to look for other maybe criteria or other things to look at. And a generalization that is very nice from Kuroda and Sujie is to say, okay, we're not going to look really at like APN functions, because when the characteristic is odd, we have PN functions anyway, so like APN functions are a little less interesting. But what we can look at is we try to like sum over like those FP linear combination of like the direction alpha, and we're going to try to solve how many x's for each images. And we have at least p, because if x is a solution, x plus alpha is a solution, and x plus 2 alpha is a solution, and so on and so forth. And when you have at most p solution, then we can kind of say that it's a generalized APN function. And it works very naturally. It's a very nice idea also because when p is even, this is exactly the APN conditions, right? So it's very nice. A little later on, Özbudak and Salajan found out that, well, actually, like this sum here is a higher order differential. Like you just take the direction alpha, you differentiate p minus 1 times, like consecutively, and you end up with this. And so since the GAPN condition is kind of like a higher order differential, they could use what I like to call the APN arsenal of tools and try to find a bunch of new GAPN functions and like say a lot of things reusing what we know about APN functions. So it's really nice work. But this talk is not about GAPN functions. So, I mean, not really. It's related, and I'll explain why. But if you're interested, I invite you to stick around for like Noordin's talk later on this session, who will also present a whole lot of new GAPN functions. So, okay, so what are we going to talk about in this talk? We're going to talk about like a slightly different types of high order differentials. So instead of taking like the direction alpha and differentiating p minus 1 times, we're going to differentiate in alpha, then 2 alphas, and so on and so forth, because why not, right? If we're looking at like generalization of APN functions and trying to make something work, why not look at this type of functions? And kind of unsurprisingly, I want to say, the result is that, well, this higher differential is exactly minus the generalized differential. And it doesn't seem completely ridiculous, but like, to be honest, if there was not this minus here, I would probably have said, okay, this is it, and I'm gonna pass. But this minus was kind of weird, and I was like, oh, this has to be like pretty easy to prove, and turned out it's not too complicated, but it's kind of curious, and it leads me to like solve a problem that that probably already exists, and I expect some of you in the room to tell me, yeah, like we already know how to solve this problem, but like I didn't find a reference. I asked some colleagues in combinatorics who also didn't know how to solve it, so like I was like, I'm gonna do it, and it's not too complicated. Like it could be like some exercise you could give to your master students for an exam or something like this. But anyway, so if you take like this higher order differential, and I'm gonna use like the alternated sum because that's how Özbudak and Salajan did it, so like I can do it too. The difference is that because we have those coefficients, 2 alpha, p minus 1 alpha, you end up with like a sum here that is of FP element that will also be in the prime field. And when you put like the plus coefficient on one side and the minus of the alternated sum on the other side, you end up trying to find the cardinal of those sets here that are described here, and where like L is kind of like where you are in the alternate sum, and U is like the element you're trying to find because you're trying to like reduce this higher order differential into this sum. Okay, pretty standard. But so the problem we're trying to solve is trying to find a collection of pairwise distinct elements of non-zero elements of like the prime field such that they sum to U. And so this is kind of like a weird problem because, I mean, it's a combinatorial problem, we're counting, but it's not quite algebraic because we're using like elements in like a multiplicative group with like an additive property. It's not quite linear algebra because like these equations, like the elements are distinct. It's not quite geometric either in my understanding because the U you take here can also be one of those elements. So like the concept of lines, I mean, in my understanding of what geometry, algebraic geometry is kind of, so it's kind of a little weird. Maybe some of you know already how to solve this. So please feel free to come to me after with a reference or like discuss. But what I did is, okay, we're going to take like a much easier set where like we're going to remove the non-zero condition here, and everything becomes like super easy. Like it's pretty trivial, right? So we're going to like relate those two and try to solve things. So the first thing we notice is that, well, if a set of cardinal L of like L elements that sums to U, like it partitions the space of all the sets of the subsets of cardinality L. And it's true for like the easy set. It's also true for like the less easy set. Now, it's completely trivial for easy set because it partitions the space in like really equal parts, whatever you take. Now, if you take the less easy set, it's also true that it partitions the space in like equal parts, but only for non-zero elements, which means that when U equals 0, it's another value that I'm just gonna denote like this, and like the partition become like this p minus 1 equal parts plus when U equals 0. Okay, so now if you take like the easy set, well, the sum of element that sums to U, well, you have like either 0 is part of the sum, and then it's essentially looking at sets of cardinality L minus 1 that sums to U, and when the U is not part of the sum. And so you can partition like this, but this property works for any U. So like the equal part here sums to like those value when U is different 0, but also when U is equal to 0. So like there is a relation between when U is 0 and when U is non-zero, and you can actually show that like the difference is -1, plus or minus 1, depending on the parity of the number of elements you sum together. Okay, and so once you have all of those, you can like it's a little. What I mean, you have to roll up your sleeve a little bit and like do some calculation, but you end up with like, okay, like this sums is actually equal at -1, and which is what we want. And when like U equals 0, well, it's -1, which is -2, and then you can also like negate this f of x multiple times. So, okay, so that was like just like the little first part of my talk, solving like this little curious problem. But then he made me think of like kind of a related question, is that actually when you look at higher order differentials, like we have like different functions, like in our case it was f and minus f, and different set of directions, which were like fp linear to each other, granted, but like more generally, like what I call like the differential diversity in a higher order, because intuitively, when you differentiate, the algebraic degree diminishes and the image set also diminishes. So like you have less and less functions that are available to you. So like it's normal that like for different functions and different multisets of directions, you're going to have some collision at some point. So like when does it happen and what does it mean? And like the what does it mean is probably it has some interest in like when you're doing cryptanalysis, but like it's a maybe, like it's an intuition. I have worked on this because I'm looking at like the theoretical point of view, and I look at for applications a little later. But like in my opinion, it's kind of a nice problem already. So what do we know? Well, we know that not all functions are derivatives, and actually a function is a derivative. It means that there's a g such that it derivates in this function if and only if the generalized differential is 0. We also know that if you look at EA equivalence or like linear equivalence, you have a first order matching, and it's kind of boring, but like it kind of works. Oh, by the way, if in the problem that I talked earlier, you're trying to solve it from like a different point of view, not like brutally by like this alternated sum, but like trying to use this, it turns out like the EA equivalence over higher order differential is kind of tricky to do, and you kind of end up to the same problem anyway. So like kind of whatever angle you try to tackle the problem, you're going to have to solve like those cardinality of sets and so on. Another thing is, well, if you look at the matching of different functions in the same direction alpha, well, we already know this. It's kind of a trivial case. And so what can we do about the problem? The problem is related, at least in the first order. So when you look at first order differential, the problem is related to like antiderivatives. And antiderivative means like it's a collection of functions that are like the derivatives in different directions of the same function h. And this can only happen if, well, each of the di's are derivatives themselves. Right? It's a moot point. And if they're compatible to each other. And like what we're interested in is only like the compatibility here in the first order, right? And so the question Salajan solved is that, okay, once we have like all of those derivatives, how do we construct the function h? The question I'm asking is, what if they're not derivatives and so they don't integrate into the same function, but how do they match? What are like two functions that match? What does it mean? Like essentially, if you have one in a certain direction, can you construct like another function and derive it in another direction so that they actually match? And so the result is, it's again kind of tedious and very computational, but the idea is, okay, we're gonna try to find like this first order matching. And so you identify the finite fields with like the vector space. You take a basis in a clever way. So you take like the directions so that in the basis. And so when you look at the algebraic normal form of the component functions of f, you can write it this way. And like you have like the coefficients of the algebraic normal form. And the result goes like this. It's like you have first order matching if and only if this sum is satisfied. And I mean, I put something under the carpet, but it also didn't fit in the slide. But you need to make sure that like the algebraic degree and the right variables match. But like this actually is essentially the coefficients of the algebraic normal forms of component function of the derivatives here. And this theorem, this result is very computational, is very constructive, meaning that now you can take like any functions, f, you differentiate it in like a direction, and then so you have like this left-hand side of the equation, and then you just have like to solve like a linear systems, and you find like coefficient for the g, and so you just constructed a function g such that you have first order matching. So it's very constructive, it's very nice, and it gives like intuition of what are the function, and so it happens. And that's kind of where I stopped in my work, so it's very much like work in progress, but the question we can say is like, can we have like higher order differential diversity? Like, what can we have like same kind of result, but when you do look at like second, third order differentials, understanding like cryptography implication, all of those also is like something that's fine, interesting, and I think would be worth looking at. And also like about like the curious problem, I mean, in my mind, the curious problem I solved is like, what if you take like any other like algebraic structure here and you try to solve this problem? For instance, like the first one would be to take like integer quotient rings, right? Or like remove an element or so on. And thank you for your attention. That's all I have to say.
Merci, Valentin. Any questions or comments for our speaker?
Have you looked in, say, in over F2 or finite field of characteristic 2, if you take the derivatives, say, in the directions of all three elements of F4? So third order thing where you 1 omega squared.
Not really. I mean, in F2, like if you look at antiderivatives, it's kind of like the case we kind of already know how to solve. I don't know if that was your question though.
No, because I'm trying to think of the example with alpha to alpha p minus 1 alpha.
Yes.
So instead of doing alpha, you do 1 omega squared.
Oh yeah, like if you take like another type of higher order differential. Yeah, there's definitely like some things to say, but like no, I haven't looked at it, but I do think there's like other interesting set, and also like you can take on subfield, you can take on like cyclotomic set and so on. And there's probably like a lot of things to say, and what are the cryptographic implication and the application of this? Like, I'm not quite sure, but like the intuition tells me that if we want to make differential cryptanalysis work in crypto systems of odd characteristic, we would have to look at like higher order differentials in a clever way. Yeah. Oh no, that's a good question. Thanks.
Any other questions or comments? Stephen?
So the first question is called subset sum problem. A subset sum problem.
Okay.
I can refer you some references.
Please.
There are some asymptotic result, and also for special type of sets, you can have exactly thing.
Okay. Yeah, like I think you're right. I think I kind of looked into it, but like the fact that you remove the zero elements was kind of weird. But like I would like to have some reference.
Yeah.
Thanks.
Any final questions, comments? No, we'll thank Valentin again.
Thanks.
We'll start again in 4 minutes.
What is this one? Oh, it goes in my ear. Can you?
When you stop, you can just stop.
Which one?
Just stop. I think. Here's the point. To the right of this point.
Okay, our second speaker is Peter Listenek, who's going to tell us about a class of APN permutations.
Thank you. I'd like to thank the organizers for setting up this really very, very nice event in this beautiful country. So my role will be a little easier because we already had a a very nice talk by C-Ham yesterday that partially was dealing with APN functions, and we just had Valentin's talk, so I'll be able to go a little faster over some of the concepts. I'll start with about 3 slides, just reviewing quickly the background and the terminology, and then I'll get to the problem to be addressed. So in C-Ham's talks and in Valentin's talk, we already had this definition of an APN function. Valentin also mentioned that when it's APN, we call it 2 uniform. And in general, if that equation has at most k solutions for any A and B, we call it K, differentially uniform. So why are we interested in this? Also was mentioned in previous talks that these functions with low differential uniformity prevent the differential cryptanalysis attack, which therefore we are protecting some of these important cryptographic primitives which are listed on the slide. So in particular, in the block ciphers, these APN functions can be used to design the so-called S boxes or substitution boxes, which are essentially the most critical parts of the block ciphers because they are the only non-linear components of the cipher. And in certain designs of block ciphers, for example, the substitution permutation networks, it's also of advantage if the S boxes are invertible. So that means if there are permutations. This is because in that case, it's possible to set up the implementation such that the encryption and the decryption can be used, can use the same hardware. So essentially, you save half of the hardware because you use the same function for both purposes. And now that we are so concerned about, for example, lightweight cryptography, where we are trying to minimize the size of the hardware, this can be very important these days. So some examples. X-cube is APN for, I did not say that, but everything what I'm doing is in characteristic 2, because, for example, Valentin also mentioned odd characteristic, but the APN, of course, are typically studied in characteristic 2. So some examples, so X-cube is APN for in all dimensions, but it's a permutation only in all dimensions. Vice versa, the field inverse function is always a permutation, but it's APN only when n is odd. So there's also this famous application of it in the substitution box of the advanced encryption standard in dimension 8. So it seems from the first 2 paragraphs, it seems that it's hard to satisfy both the evenness of the dimension and the APN permutation property. So famously, this was achieved in dimension 6, but in no other even dimension yet. C-Ham mentioned yesterday that this is considered to be the big APN problem. So I'm not solving the big APN problem. All I'm doing in this talk is actually in R dimensions, but I'm finding some hopefully new APN permutations in the R dimensions. So it's like always in mathematics, when we are trying to solve some very hard problem, maybe before doing that, we try to solve some easier instances or easier variations. Maybe it gives us more insight and we are better prepared to attack the harder problem. So This of course, this API permutation in dimension 6 is very famous. You probably have all heard about it. You probably have some idea how it was done. The method was very particular to dimension 6. They did not have any kind of general consideration, really. It's essentially a computation in a sense, what they did. So with my student Ben Chase, we wrote what I would call a kind of formalization of this method, because the original paper in dimension 6 is really just working with that one particular example, essentially. So they don't do any like formal consideration. So we kind of formalized the method. We described how it would work in general. And there's this paper that I'll call CL later on. So in this paper, in this 2022 paper, we published a formalization of the method, several results on it, but we did not really look on what it actually produces. So if you actually use it, what will it give you? So this is the purpose of this talk, that I actually only now started, so 3 years later, and started to do some computations with these methods that we found previously, and I looked what they are giving. So for the formalization, we need to define the Walsh coefficients that was in Seham's talk. We say that a pair AB is Walsh 0. And if this vector space is n-dimensional, then we call it a Walsh 0 space, or WZ space of that function f. So these WZ spaces will be very important. They're important for the reason of the second proposition on this slide. The first definition is just what you would expect, that if you have two such WZ spaces and they intersect only at the origin, you call them trivially intersecting, or TI, pair of functions. So that's just a terminology. The second proposition really is when I said that we formalized the Browning, Dillon, and two more. I'm sorry, I had the reference at the end. Their method of used in dimension 6, this is essentially that formalization. That if you have a function that for which you possess two trivially intersecting Walsh 0 spaces, then this actually is constructive, the proposition. You can actually, if you have those two spaces in your hands, you can actually find a permutation that's CCZ equivalent to that original function f. So the CCZ equivalence was defined yesterday by Sehem. So how did they use this in dimension 6? They started with a function f, which they later called Kim function. Kim is the first name of one of the authors, Kim Browning, I think. So they started with that. It's an APN function in dimension 6, but it's not a permutation. And they essentially found two trivially intersecting WZ spaces. They don't call it that. They use the equivalence with linear codes, and they do everything in terms of those codes. But you can also formalize it in this way. And so the CCZ equivalence preserves the APN property. And therefore, if you use this proposition to find, you can find, if you possess those trivially intersecting WZ spaces, your function is already APN, you can find an APN permutation that way. And that's what I did in the dimension 6. So they started with a Kim function. So what happens if you start with some other functions instead? And that was a subject of many papers ever since that 2009. Since we are at Fq16, I should mention that that result was presented at Fq9 at this conference, also at the 9th edition in Dublin. So many people, of course, got interested in this and started with different functions f and tried to somehow do a similar thing. Was not really successful in even dimensions yet. So as I said at the beginning, so today we do an easier version of it. We look at what it does in all dimensions, and specifically if you start with the Gold functions as your starting functions. So the Gold functions will take place of this Kim function f. So as I mentioned at the beginning, these are APN in all dimensions. We, in this talk, we only look at them, at the Gold functions in odd dimensions. Now, since there are permutations in odd dimensions, they possess these two trivial WZ spaces. The Z, sorry. Oh, sorry. The Z0A is a WZ space of all functions. Any function will have the WZ space, and the Z0B characterizes a permutation. So if this is a WZ space, if your function is a permutation, then it has this WZ space. So we need lots of WZ spaces and trivially intersecting pairs of them to do what we want. So let's get that done first. So there is fortunately the voice zero criterion for the Gold functions, fortunately, is quite simple, and that actually enables a lot of what we are doing. So it was found by Gold in the context of finding permutations with good autocorrelation properties. Sequences with good autocorrelation properties. So there's the characterization. It doesn't appear exactly like that in the Code paper, but essentially it's there. There were some subsequent papers that filled in some more details, but it's essentially comes from that paper. So you see the condition is relatively simple, so that helps us a lot. So we need this TI pairs of the WZ spaces. So in this paper with Ben Chase in 2022, we found several constructions of the TI pairs of the voice zero spaces. So they are expressed in that paper as 4 propositions. Propositions, of course, are quite so CL will denote that paper. So the propositions, of course, are quite technical, but they are also very explicit. You really can just use them as is, okay? They are like full recipes. So they typically are parameterized. They have typically 1 or 2 parameters from the field of order 2 to n, and they may have parameters from F8 if the dimension is divisible by 3, and you have F8 as a subfield. So I'll just go quickly through them. They are in the paper if you want to get them. So there are 5.1. It's the numbers from the paper: 5.1, 5.2, 5.3, 5.4. So these were published in the paper, and we haven't done anything with them really since, because I was busy with many other things. And so finally, I just got around to actually coding them and trying to do some computations and what the computations gave. So to explain what the computations gave, it's good to recall the EA equivalent. So again, that was in Seaham-Stokes, also in Valentin-Stokes, so I'll just skip it. And there are properties which are preserved by the EA equivalents called EA invariant. Now the EA invariants can be used to show that certain two functions are not EA equivalent. Because if the functions have different values of the invariants, they will not be EA equivalent. So that's what we use. So as I said, I did some computations with these propositions from the 2022 paper in dimensions, odd dimensions up to 15. Because the parameter spaces are very large, I sampled the parameter values randomly instead of, because it was not possible to exhaustively check all possible parameters. The EA invariants that I use to check whether the functions possibly are EA inequivalent, the algebraic degree and the minimum degree, the minimum algebraic degree. The minimum algebraic degree is the minimum, as you would think, is the minimum algebraic degree of any component function of the vectorial function. So the main result is in the bottom that for the proposition 5.3, it's not so surprising that it's actually that proposition 5.3 that produces the new APN permutations, because it's the kind of richest one. It has actually 3 parameters. 2 parameters are in the domain of the function, and 1 parameter is in the subfield F8, so it's required that the dimension is odd multiple of 3. And how do we know that we have new APN permutations? It's the algebraic degree tells us. So we are finding, or I am finding, should I say, APN permutations of algebraic degree 4. So whereas the goal functions that we are starting from have algebraic degree 2, and the compositional inverse of the goal function, which also is CZ equivalent to it, and it's also an APN permutation, of course. So that has degree, algebraic degree n plus 1 over 2. So when n is greater than 3, the 4 will be different from both of these values, and therefore these APN permutations of degree 4 are not EA equivalent to gold or gold inverse. So it's still in progress very much. So what, of course, is kind of obvious what I would like to do from here on. So it would be nice to have some invariants, some other EA invariants that could be employed for assessing the EA equivalence. Because the known invariants either are very hard to compute, some of you may know that, right? They have been reported to take weeks to compute, one case, or they are not suitable, because many invariants are specifically designed for quadratic functions, which we have degree 4 here, so they don't really apply, and or they are specifically designed for even dimensions, which again does not apply. So we are kind of looking for more suitable EA invariants to use, and of course find a formula. So it's now very tempting, now that we know that these things exist, to actually write them down as a formula. So for the references, the dimension 6, there are actually 2 papers. So the second one is the proceedings of Fq9, so that one is more known. But if you really want to read on this, it will be good to know that there's also the first paper, which is lesser known, but it's actually much longer and has much more stuff in, and also has a different set of authors, by the way. The third paper is the one that I've been using. The fourth paper is just in one sentence. What people tried a lot was to generalize that Kim function that the Dillon group started with. They started with this Kim function and turned it into a permutation. So people tried to generalize the form of the Kim function. So there's a certain quadrinomial that's a natural generalization. And as a second result with Ben, we actually proved in 2021 that if you start with these Kim functions, Kim-type functions, then they are APN only if they are affine equivalent to gold. So actually you are not getting anything new. I should say that this is not only our results. It sounds, it was kind of we happened to be the final step. So we actually closed that question, but there were at least 5 or 6 previous papers that we were using, okay? So I don't want to own this, but we just happen to be the ones who closed the door. Okay, thank you for your attention.
Thanks very much, Peter. Any questions or comments?
Thanks for the talk, very nice. I was just wondering if we can still try to find monomials as APN.
Yes, I mean, the functions that I'm getting will not be monomials. I mean, the monomials have been classified. So the monomial APN functions are known, all of them.
Oh, all of them?
Oh, yeah,
Okay,
that's easy. Okay. Yeah. There's about 5 groups. There's, Sihan would know this better, but it's Gold, Kasami, Welsh, Dobertin. I missed one. Yeah. Yes. Also, of course, with the monomial functions, there is some scare that because they have just one term, this could be, Sihan is nodding, so I'd probably say what I'm saying. It's spelled out, for example, in Claude Carlet's book, that this may lead to what they call an algebraic attack, because, since your formula is so simple, for the APN functions, you may be able to run an algebraic attack against it. So in fact, it doesn't harm. You never implement the S boxes as computations, of course, for many reasons. Even if your formula has 1,000 terms, it doesn't matter, because you implement the S boxes as lookup functions. That's for several reasons. A, that they are constant time. You want all this constant time, right, to avoid the timing analysis attack. And also it's much faster, the lookup table, than the computation. So it actually, like for the actual implementation, it doesn't matter whether your function is monomial or whether it has 1,000 terms.
Oh, okay. Yeah, but maybe is there any, I don't know, guess to look for certain families?
I have some. Yeah, I would say I have some knowledge that's not on the slides. Yeah, it's work in progress. So, but I have some hope that I know something that could be used. Yeah. Mm-hmm. Thank you.
Okay, we'll continue with our third speaker, Kirpa Garg, who's going to speak about revised boomerang connectivity and other words too.
So, thank you. First of all, I would like to thank the organizer for giving me this wonderful opportunity to present my work here. Today, I am going to talk about the notion of revised boomerang connectivity tables and a very well-known notion of difference distribution table. So this is a joint work with my PhD supervisor, Sartajul Hassan, Constanza Rera, and Pentelamon Stanica. So in the previous two talks, we have already seen about the differential uniformity and APN functions, and also in the yesterday talk by Professor Singham. But still, I want to define a little bit about the difference distribution tables. So, okay, yeah. So as Peter mentioned, that the substitution boxes or S boxes, they play a very important role in designing, modern box ciphers. So mathematically, S box is nothing but a function from finite field to finite field. And there are many attacks that are possible on these block ciphers. One of the most efficient attack was introduced by Biham and Shamir in 1991, which is known as the differential attack. And further, to measure the degree of resistance of these S boxes or degree of the resistance of these functions against this attack, Nyberg proposed the notion of the differential uniformity. So mathematically, we can see how this happened. My talk will be based on the finite fields with the even characteristic. That is, Fq will denote the finite field with 2 to the power n elements, where n is a positive integer. So if you have a function f from finite field to itself, and if you take an element a in Fq, then the derivative of this function f in direction a is nothing but given by this expression f at x plus a plus f at x. And we can do this for every element a of f finite field Fq. We can find the derivative. And if we have two elements, we can choose two elements from the finite field Fq, A and B. Then corresponding to those two elements, we can always find the number of the solutions of this equation f at x plus A plus f at x is equal to B. So what we are doing basically, we can take A as rows and B as column. So corresponding to Ath row and Bth column, the entry is nothing but the number of solution of this equation f at x plus A plus f at x is equal to B. And the differential uniformity is defined as the maximum of these entries of the difference distribution table. Yeah. And we have to obviously exclude the first row that corresponds to A is equal to 0. Because if A is equal to 0, then we are in even characteristic fx plus fx is equal to 0. Obviously, for A is equal to 0, B is equal to 0, you will get the that every element of the finite field is satisfying this, and then the maximum number of the solutions are basically the cardinality of the finite field, and then there is no sense of talking about the maximum here. Also, over the even characteristic finite fields, if the differential uniformity always came in the even number, because if x is a solution, then x plus a is also a solution of the equation fx plus a plus fx is equal to b. If a function has differential uniformity delta, we will say that it is a differentially delta uniform function. Like if it has differential uniformity 4, we will say that it is a differentially 4 uniform functions. And we already know about the APN functions. So these are the functions with the best possible differential uniformity over the finite fields with the even characteristic. And I think I don't need to say much about this. The functions with the low differential uniformity are the desirable one. However, in 1999, later, it was noted by Wagner that there is another important attack, which is known as the boomerang attack. And it basically, it is not easy to find a differential for the complete, so they divided it into two parts. So it was noted in 1999 by Wagner, and they introduced in the terms of the boomerang attack. And Similarly, just like the concept of difference distribution table and differential uniformity, we have the concept of the boomerang connectivity table and boomerang uniformity. So it was introduced by Sid, Huang, Perrin, Sasaki, and Song in 1999. And again, it was not yet enough in some settings. Like in multiple round settings, the boomerang attack was not sufficient. So it was again noted by Wong and Perrin, and they highlighted the need of some another tools which they stated as boomerang difference difference table BDT, and along with its variant BDT dash. So the example where they have noted this is the 2-round AES, where they found the need to introduce these tools. Later, Delaunay, Durbus, and Wevril, sorry for the pronunciation, they renamed these tables as upper boomerang connectivity table and lower boomerang connectivity tables, basically to emphasize on the upper characteristic and lower characteristic respectively. So as you can see that this notion is like in 2020, 2019, and the difference distribution table was very well known from 1990s. I know there are still many open problems like big APN problems. There are still many functions. We can find very less functions with low differential uniformity. But what we are doing exactly, we are finding these tables in the characterizing them in the terms of difference distribution table. So there are many functions we know about their difference distribution table entries, and we are establishing a relationship between them. So first of all, mathematically, I would like to define what we mean by this upper boomerang connectivity table and lower boomerang connectivity table. So if we have a function over finite field f to n, then for any 3 elements a, b, and c, I can write, we can define the LBCT of the function f at a, b, c is basically number of solutions, number of x in the f to n, for which there exists at least one y, such that x plus y is equal to b, fx plus a plus fy plus a is equal to c, and fx plus fy is equal to c. So originally this definition was introduced for the permutations. So we have generalized it to any function over finite field. Similarly, we have the definition of the UBCT here, that we are again counting the number of x in the finite field such that there exists at least one y, so that all of these equations get satisfied. So this is how LBCT and UBCT are defined. So now this is basically our result. So in this you can say that if f is a differentially delta uniform function, from differentially delta uniform means that it has the maximum of the DDT entries is delta, and we know because we are over the even characteristic, so the DDT entries only can take even values like 2. So if DDT, if I take 2 elements B and C from the finite field, then its DDT is, if 2k, it's obviously even. So it can be k can be 1, 2, up to delta by 2 because it is differentially delta uniform. Okay, and this DDT is nothing but the number of solution of this equation f at x plus b plus fx is equal to c. So let this set denotes the number of solution of this equation. Right? Then for any a, b, c in the finite field, the LBCT of the function f at a, b, c is basically the DDT of the function f at b, c if b is equal to c is equal to 0 and some other conditions are there, a is equal to b and ab is not equal to 0 or so on. And in other terms, it is 4 times L. So this is the interesting part because it took a little time to get us here. So here you can see in this condition, if A is not B, AB is not equal to 0 and DDT is 2k, which is 4r or 4r plus 2, r is an integer. So here I am not talking about the DDT 2. I am starting it with, r greater than 0 is an integer, so I am starting it with 4. So if we have the DDT 2, we get that then either this should hold. A is equal to B and AB is not equal to 0. So that case is already being done here. Here we start with the elements having DD4. And similarly, we found a very interesting relationship that if A belongs to these sets, intersection of this set, and so on, where these sets are basically based on the solutions of this equation, then we know we can express LBCT in the terms of DDT here. So it might look a bit technical here, but we can use it, to explicitly determine the LBCT and UBCT entries for various well-known functions. So I have one example included in my next of some slides. Like we have done it for Gold function, Kasami function, Brecken-Leander function, and so on. So similarly, we have here a relationship of upper boomerang connectivity table with the DDT entries, and there is one more table which was also renamed later by Delevani, Derbez, and Vivril. It is known as the extended boomerang connectivity table. So this was first initially introduced by Bocquereau, Heon, Lilleman, Mundell, and Minier, and it was named as FBET, Feistel Boomerang Extended Table for Feistel ciphers, and Boomerang Extended Table for SPN ciphers. Later, they renamed it to Extended Boomerang Connectivity Table. So in this table, again, we are counting the number of solutions of some equations over finite field. So basically, my work is completely based on counting the number of solutions of equation over finite field, which is not that easy sometimes and not difficult that sometimes. So we have also, found the relationship of DDT entries with EBCT as well. And again, here's a theorem. If f is a differential delta uniform function and DDT of CD is 2k, k can assume the value from 1 to delta by 2. And this is the solution set. Then the EBCT of the function f at a, b, c, d can be defined in the term of DDT here. Moreover, you can see that here I am taking this tuple a comma b belonging to this set ui1 j1 intersection and so on. So there seems to be some relationship between this EBCT and LBCT, because this set here is somewhat containing the images of f, and here in UBCT we are taking the initial element yi plus yj. So we also noted this thing that might be these tables are interconnected. So maybe we can get LBCT and UBCT in terms of EBCT or vice versa also. But to first of all, to apply it, we start with the APN functions. So if you are having any APN function over F2n, then you can easily get these EBCT, LBCT, and UBCT entries in terms of their DDT entries. So, and the best possible value you can see, because DDT can be 2, so it can, EBCT, UBCT, LBCT can also attain the best value as 2 here. So this is for the APN function, and we also computed for them for some well-known function like Gold function. So we are here taking differentially for uniform Gold permutation. That's why these are some conditions that if x to the power s plus 1, GCD of s comma n is equal to 2, and this is s is odd, then we explicitly get these values and these conditions using the DDT entries. Similarly, we have the UBCT of the Gold function and EBCT of the Gold function. So I would like to summarize by saying that this is our work. In this, we have basically found an intriguing connection between EBCT, LBCT, and UBCT and the DDT entries. Moreover, we were able to characterize EBCT entries in terms of LBCT and UBCT entries. And for some of the well-known differentially for uniform permutations, for which we know how the DDT entries behave, we were able to compute their EBCT, LBCT, and UBCT entries using our results. Also, it is not mentioned here, but we have studied these notion, the equivalences for these notion. Would they be preserved or not under extended affine CCZ and affine equivalence? If anyone is interested, they can go through the complete paper. And thank you.
Thanks very much. Any questions or comments for speaker?
Yeah, thank you for the talk. Now my question is very simple, because in your theorems you start with this function f with a certain, it has to be a delta uniformity with a, do you have examples of f? Like the functions f? Maybe they are known, because look to the theorem, like maybe back. Yeah, here, like this. You start with f be a differential delta uniform function, and you know that the dt of f CD is 2k. So do you have an example of a function that satisfies this? Like,
yeah,
they are really known, just
no, because this was done for the general. Yeah, for the gold function, like I implemented this. If we start with the gold function, it is differentially. I started with differentially 4 uniform gold function, and then I implemented this theorem, and we can get the values explicitly. This is for a general function. If we start with any function which is delta uniform, so
Yeah,
delta can be anything, right?
okay. No, I just asked about a explicit example of f. F is gonna be like this, like a, don't know, polynomial, which ones are. Okay, it's okay. Huh?
Yeah.
Okay, thank you. Yeah, you can.
Thank you. I just wanted to ask you, so there is also another notion of uniformity, when you put some C, some coefficient, instead of taking the normal differential, you take a differential with respect to some constant C. So you take f of x plus a minus C times
C
f. Okay.
differentials?
Yes, exactly.
Yeah.
So do you think that there is a connection also for that type of table, those types of tables, and so can you mimic your approach in order to get some connection?
With the CDT?
Yeah, C not equal to 1. Yeah,
because
yeah.
it will be the same.
Yeah,
Yeah,
sure.
yeah. So I have not, I have not gone through it, but I have not gone through it. Maybe I can look at that. I don't know. But there's a connection with, boomerang connectivity table, BCT. It was given in the original paper, direct connection with the BCT, and we were able to do it for DDT, but I haven't gone through the CDDT. I think you're talking about the C difference distribution table. Yeah, but I don't know right now. I will look into it. Thank you.
Thank you very much. I'm wondering if you know a paper of me and
yes. You have done this for multiplicative inverse function.
Yes, it was published in 2025 or so.
Yes.
So there is overlap or
no? No. Actually, you have
because I studied on this with.
No, because
I mean, not all. Maybe I don't know.
No. We have also, mentioned your paper in our work also, but there's no overlap.
Super.
Yeah. You have done it for completely permutations. We have done it for, arbitrary functions, and we have mentioned them in terms of DDT. And I think there was one more paper by Neon Lee and all. They have also done for the multiplicative inverse functions. So I don't think there is any.
Okay. Because you didn't mention at all, so I wondering is you know it just.
I know.
Okay, super.
I know very well.
So
about that.
okay, I will be happy to read this one.
Yeah.
Okay, thank you so much.
Any other questions or comments? If not, let's thank the speaker again. We'll continue in 5 minutes. Okay, so we'll continue with our final talk of the morning from Nuruddin, who will speak about generalized APN functions of the lowest algebraic degree.
So, hello, everybody. Thank you very much for being here. So, today I'm going to present you our work, me and Valentin Suder, about generalized APN functions of the lowest algebraic degree. So here we are going to talk about generalized something APN functions. So let's start first by introducing APN functions. So we take any function over the binary field f2 to the power of n. Any direction, we define the derivative of f in the direction alpha as the difference of the f of x plus alpha and f of x. And a function f is said to be APN if this equation here has almost two solutions for every non-zero direction alpha and beta. Kuroda and Tsuji gave a generalization of this notion in 2016, and they defined, they generalized it over over fields of odd characteristics. So we take any function f over a field like of degree n, and and f is said to be a GAPN function if this equation here has almost p solutions for every non-zero alpha and beta. In 2021, Özbudak and Salajan after that, this is actually a generalization of the APN notion. So when p is equal to 2, this sum here is just the discrete derivative of f in the direction alpha, and the JAPN notion is just the APN notion. And Özbudak and Salajan noticed that for any direction alpha, this sum here is just a higher order derivative of f in the direction alpha. So we just apply the discrete derivative alpha p minus 1 time. And so they called this sum here the generalized derivative of f in the direction alpha. So the discrete derivative and the generalized discrete derivative have an impact over the algebraic degree of functions. An algebraic degree of a function f is just the multivariate degree when we see the function as a vectorial function over the space fp to the power of n. And for any direction, if we apply the generalized derivative in the direction alpha on f, it will reduce the algebraic degree of f by p minus 1. And in particular, if the algebraic degree of f is p, then for any direction, the generalized derivative of f in this direction has an algebraic degree less or equal to 1. That means it's either a constant or an affine function over fp. And Kuroda and Tsuji showed that any JPN function has an algebraic degree of at least p. So we are going to study the functions of algebraic degree exactly p, the lowest algebraic degree possible, and especially what we call the generalized and Dombovsky-Ostrom polynomials. They are just homogeneous polynomial for algebraic degree p, and if we replace p by 2, they are just quadratic functions and homogeneous quadratic functions. So I will first present our results for the monomial case. We take a monomial function of algebraic degree p. An example is when if x is like that, if we sum the red coefficients, we will just have a 5, and this is just the algebraic degree. And for any direction, alpha, the generalized derivative of f in direction alpha is just like that. So we have a 3, 1, and 1 here that appears. An important result about those functions is given by Uzbudak and Salajan in 2021. So we take any generalized Dombovsky-Ostrom monomial, and the result is that this function is GIPN if and only if this GCD of this and this term here is equal to x minus 1 in FP of Z. So we are going to study, we are going to fix this term here, and we are going to search for n such that we have this equality. First, remark that z to the power of n minus 1 can be factorized to this like this, where QD of z are just a cyclotomic polynomial of order d. And an interesting fact about this polynomial is that we know the degree of every irreducible factor of QD is just the order of P modulo D, where the order is just the smallest m, such that this is true. P to the power of m is equal to 1 modulo D. And the left part of the GCD was just this here. And if we evaluate this polynomial in 1, we will have this sum that will be summed to P, and this is just 0. So this polynomial can be represented as this, where U is the multiplicity of 1 as a root in this polynomial. And if here, so if every QD here is prime to V of Z here, we will have this equality. This GCD will just be this one. So if U is equal to 1 or M is equal to 0, we will have this equality. And so the function f, that the monomial function that I presented first, will be GIPN. I will not go to the proof of our results, but I am going to show you what we have obtained from that. So we take a function f, monomial function of algebraic degree P. We have the following result. So if the extension degree is like that, we have a condition over L here, the Hamming weight of E, and the order of P modulo QE for the function f to be GIPN. In fact, the conditions depends only on the primes in the prime factors of the extension degree. But with this theorem, we cannot obtain extensions of even degrees, because if there is a 2 here, the order of any ordered prime modulo 2 is just 1, and this is just, we will just have L equal to 1. So we have the second result here that gives us extensions of even degrees. But we add a condition, is that when we see this here, there exists two monomials in P here that have an exponent of different parity. And the second theorem is that if n is equal to 2 times n, where n is like that, and we have the same condition as the previous one on n, then f will be a GIPN function over all this, over the field of extension of extension degree n. The last result is a specific case, a full characterization of this kind of functions. So this is a monomial function where the exponent is of Hamming weight 3. And if we express n like that, p to the power of alpha times n, where the GCD of n and p is equal to 1, then we have this result. F is GAPN over fp to the power of n if and only if one of the conditions here, or here are true. As an example, if we take A0 equal to A2 and alpha equal to 0, we have this function. And these functions are JPN for every extension degree n greater or equal to 3, and n is not divisible by p. Now I am going to present you our results on multinomials, but now we are supposing p odd p. First, we have a formula for, so we take any generalized Dombovsky-Ostrom function f, and any direction, we can obtain the form of its generalized derivative. It's just like that, and it's a linearized polynomial, and we have the coefficients here are just of this form. And we have a very good result given by McGuire and Shiki about those polynomials, is that if we have a linearized polynomial of p degree L, where the dominant coefficient Fl is not 0 and the less coefficient is not 0, then F has p to the power of L rows in this extension field if and only if this matrix here is equal to the identity. So if we take L equal to 2, then we only have to prove that this equality is not true to have an interesting thing, P solutions. And some remarks that the determinant of this matrix only depends of F0 and Fl. And if this is not equal to 1, then this matrix is not equal to the identity. And we have the following JPN functions. So we take this binomial, and if the norm of lambda times k over d is not equal to 1, then f is a JPN function over fp to the power of n. As an example, if we take k equal to d, then this function is these functions are JPN for every odd positive integer greater or equal to 3. So to conclude this talk, we have we gave a new classes of monomial JPN functions up to a generalized affine equivalence given by Kuroda and Tsuji in 2016, and new classes of multinomial JPN functions. And now we are wondering if we to find another new JPN functions, and we are wondering if there are for the possible applications of these functions in cryptography and coding theory. So thank you very much for your attention.
Thanks very much. Any questions or comments? We'll thank the speaker and all of our speakers this morning.
Thank you very much.
Oui, c'est ça. C'est pour que ça puisse science, que ça prend une coefficient égal à 1.
On peut prendre. En fait, c'est un.
En fait, ça dépend où il
Vraiment. Et en fait, ça donne.
Parce que quand tu dis monomial, ça veut dire AX à la
Oui, en fait, si tu regardes bien, parce que le GCD, lorsque U est égal à